250 million years ago, Earth came terrifyingly close to becoming a dead planet. Over 90% of species vanished in the greatest extinction event in history. But what could trigger such unimaginable destruction? In the next few minutes, we'll uncover the hidden forces behind the deadliest die-off our world has ever faced. If you find this journey fascinating, please like, subscribe and share. Thank you for watching. Now, let's begin. The supercontinent rests, immense and silent, its mass stretching across nearly all of Earth's surface. From pole to pole it holds deserts, mountains and shallow seas, an arrangement that seems stable, though its very scale breeds its own fragility. Pangaea, as it is later named, locks together the continents in a vast sweep of stone. The interior lies far from any ocean's moderating touch, and there the land grows arid under sun that passes across endless distances of bare sand and scrub. Rain clouds rarely reach so far inland. Where water lingers, ephemeral rivers run wide in season and vanish to dust again, leaving behind braided patterns across the soil. Winds move unhindered across these open plains, sculpting dunes that drift slowly like great waves of pale sediment. Along the margins of this landmass, seas remain warm and teeming. Shallow waters stretch far across continental shelves, creating wide habitats for marine communities. Corals, sponges and reef-building organisms raise intricate structures where sunlight falls clear through the upper layers of water. Brachiopods fasten to rock, ammonoids drift with coiled shells, and trilobites, though fewer than in earlier ages, still creep along the sea floor. Fish with armoured scales pass through shoals of smaller creatures, and predators follow patterns that seem timeless. The sea is not empty but rich, shaped by long evolutionary branching since the Cambrian dawn. Reefs build themselves into immense limestone factories, filtering carbon into stone, crafting layer upon layer that stores the rhythm of shallow seas. These ecosystems are resilient to normal fluctuation, able to bend with shifts in temperature or nutrient supply. Yet in their stability lies a hidden vulnerability, for they depend on balance, and balance on Earth is always temporary. The air, though warm, remains breathable and clear. Forests cover belts nearer the coasts and along rivers that carry water to the ocean. Glossopteris trees stand in southern lands, their broad leaves dropping into layered mats that later turn to coal. Conifers grow tall in other regions, while seed ferns and smaller shrubs spread beneath. Insects hum within this vegetation, their wings glinting in the sun, and reptilian synapsids, ancestors of mammals, move between shade and open ground. Herbivores graze and browse, while predators lie in wait. Life is diverse, confident, and unknowing of what is to come. Fossils from these times show ecosystems established and widespread, yet within them lie clues of stress building slowly. Small changes appear in growth rings of trees, in chemical signals of shells, in subtle losses that do not yet form a pattern large enough to see. Only took the coincidence of continents locking into one to create so vast a dryness. Only took the slow rise of mountain belts to reshape winds. Only took the position of seas to draw warmth into shallows. These quiet geographies set the stage for later collapse. Warmth arrives, but forests depend on water. Reefs thrive, but their builders depend on chemistry. Abundance persists, but it depends on thin lines of balance that can tilt with force from below. Sediments deposited in these years tell of seasonal rhythm. Varves, thin layers of clay and silt, record rains that arrive and vanish. Fossil pollen gathers in basins, marking the spread and retreat of plants through time. Coal seams continue to form, testifying to thick vegetation, yet their thickness grows irregular. In some places, peat formation falters, perhaps reflecting the creeping aridity of interiors. These details stand as whispers that climate is not static, even as ecosystems continue. Oceans carry their own quiet warning. Beneath the surface, deep water is already limited in oxygen. In normal conditions, circulation renews it, bringing oxygen from the atmosphere into depth through overturning currents. But in warm climates, stratification strengthens. Warm water floats over cooler layers, and mixing weakens. Even before great eruptions arrive, the seas beneath Pangaea trend towards stillness, the abyss holding less breath. Marine animals that depend on oxygen-rich waters cluster closer to surface zones, their ranges narrowing in ways unnoticed at the time. It only takes the right push to tip this balance into collapse. The mystery is not that ecosystems thrive under strain, but that they thrive for so long, as though unaware of the fire that waits beneath. The stillness of stone conceals magma rising in chambers below Siberia, silent for now but gathering. Already, mantle plumes stir deep within Earth, preparing pulses of molten rock that will one day break through crust in volumes almost beyond imagining. Yet in this early moment, life lives as if no change lies ahead. There is irony in this calm. This supercontinent brings vast deserts, but it also allows migration without ocean barrier, spreading lineages widely. Forests suffer inland, yet along coast they flourish, binding soil in root systems thick with shade. Seas grow warm and stratified, but they feed coral and sponge reefs to their greatest expansion. Diversity peaks in many groups at the very edge of collapse. It only takes a shift in chemistry to undo what countless generations have built. In rock outcrops that preserve this time, paleontologists find patterns of optimism written into stone. Abundant fossils show flourishing communities. Ammonoid shells lie scattered across ancient seabeds in tangled clusters, indicating seas alive with predators and prey. Petrified forests show growth unbroken by catastrophe, their rings broad and steady. Yet between these layers, thin seams mark intervals of stress, perhaps from volcanic pulses smaller than those still to come. A rise in mercury traces through sediments, not yet widespread but present. These signals appear like faint shadows of a greater disturbance waiting in the near future. The slow irony is that abundance is always most visible just before disappearance. Reefs stretch farthest before their collapse. Forests thicken before their dieback. Coal seams accumulate thick layers before they vanish. Diversity peaks just before it falls away. This pattern repeats through Earth history, a rhythm of expansion and sudden quiet. The Permian world follows this pattern, though those who lived within it could not know. The atmosphere carries a peculiar steadiness. Carbon dioxide levels are higher than in modern pre-industrial times, but not yet catastrophic. Oxygen remains near levels sufficient for forests and animals alike, yet the balance is fragile. A single source of gas, large enough and sustained enough, can shift the climate into a new regime. That source, hidden beneath Siberia, is preparing. The continents rest, seas warm, forests grow, and ecosystems thrive in their accustomed rhythms. The silence of stone deep beneath prepares its exhale. Only took the arrangement of one supercontinent to draw land away from ocean. Only took the rise of one plume to summon basalt across half a continent. Only took the layering of one sea to hold oxygen from its depths. What seems immovable proves delicate. What seems permanent proves contingent. In this calm before the fire, Earth holds its breath, storing within stone and sea the conditions that will soon unravel. The stillness of Pangaea appears absolute, yet beneath it lies motion. The continents drift slowly upon convecting mantle, their shapes imperceptibly changing even as their union seems complete. The ocean around them, Panthalassa, is immense, circling nearly the entire globe, and within it deep currents move in cycles longer than human imagination can measure. Such currents decide whether deep waters breathe or suffocate. They shift with temperature, salinity, and the pulse of climate. In these years they lean towards stratification, not collapse, but the seeds of collapse wait. Fossil spores, pollen, and shells continue to accumulate in sediments, quiet witnesses to a world unaware of its future. Each grain of dust falling on a desert dune, each shell fragment sinking to a shallow seafloor, each ring laid down in a growing tree is part of a record that endures long after life itself ends. Through these layers, modern science can read the approach of extinction, though the living creatures of the time know only abundance. Warmth arrives, oxygen leaves, forests spread, soils thin, diversity peaks, vulnerability deepens. Only took the quiet arrangement of stone and sea to prepare a stage for collapse. In this world of deserts inland and seas along the margins, of forests in belts and reefs in shallows, the Permian earth appears steady. Yet it is already leaning towards silence. In the northern reaches of what will later be called Siberia, the crust begins to split. Mantle plumes rise upward from deep within Earth, hot material that pushes against the rigid lithosphere until cracks form. Through these fissures, molten rock ascends, immense volumes of basalt flooding across the land in eruptions of a scale rarely repeated in planetary history. The Siberian Traps, large igneous province, begins with fire, not in a single burst but in countless fountains of lava surging from fissures that extend for hundreds of kilometers. Sheets of basalt spread outward, stacking one upon another until the pile measures kilometers thick. The total volume that will eventually be emplaced is measured not in mountain chains, but in whole provinces, millions of cubic kilometers of solid rock that once flowed as liquid. To imagine its scale is to imagine half a continent buried in firestone. The eruptions are not sudden in human terms but relentless in geological time. Each event may last years or decades, yet between them lie pauses where the land cools only briefly before fire resumes. In some phases, eruptions release lava flows that run for hundreds of kilometers across plains, filling valleys and burying rivers. In other phases, intrusive sills and dikes penetrate sediments rich in coal and organic matter, heating them and driving gases into the air. The tempo is pulsed, a rhythm of outpouring followed by silence, then renewed outpouring again. It only took a mantle plume meeting the right crustal setting to sustain such volume. It only took persistent fractures to keep pathways open. It only took repeated intrusions to amplify the chemical burden. The sky darkens above these eruptions. Volcanic plumes rise into the stratosphere, carrying aerosols, sulfur and particulates that scatter sunlight. For brief intervals, Earth cools under their shadow, only to warm again as greenhouse gases accumulate. The paradox of eruptions lies in their duality. Short-term cooling from particles and long-term heating from carbon dioxide. Forests experience years of dim skies, then centuries of rising warmth. Rivers swell with ash-laden rains, their waters running black with eroded soil. Lava plains radiate heat that reshapes local climates. Animals retreat where they can, but over such timescales there is little escape. Evidence remains in the rocks themselves. Layers of basalt stretch across northern Russia, their thickness testifying to repeated outpourings. Within them, paleomagnetic signatures record ancient orientations of Earth's field, helping geologists piece together the sequence of flows. Interbedded sediments show intervals of quiet, with fossilized soils and rivers marking pauses between eruptions. Thin seams rich in mercury lie within clays elsewhere on the globe, signals of volatile release carried by atmosphere and deposited far from the source. Nickel anomalies point to deep mantle material enriched in metal. These details align with the story of eruption on continental scale. The greatest uncertainty lies in how quickly gases were emitted. Was it a steady exhalation over millions of years, or were there bursts of degassing tied to specific phases? The answer matters, for life can endure gradual change but falters when thresholds are crossed quickly. Some zircon crystals dated with uranium-lead techniques indicate pulses lasting less than 100,000 years, short enough to overwhelm ecosystems unprepared. Others suggest more protracted episodes, spread across nearly 1 million years. The truth may be both. Sustained background activity with moments of catastrophic release. 3 ironies emerge from this fire. It only took rock long buried to alter air and sea. It only took eruptions from deep time to dictate the fate of creatures on the surface. It only took the transformation of landscape into basalt plain to prepare oceans for suffocation. Warmth arrives, forests falter, ash falls, soils erode, lava spreads, seas change. In the fossil record, hints of disturbance multiply. Species already stressed by climate in Pangaea's interior face new challenges as rainfall patterns shift under skies filled with aerosols. Plants sensitive to light struggle in years when sulfur haze dims the sun. Soils lose cohesion as vegetation thins, and rivers carry more sediment to the sea. Near the eruptive center, whole ecosystems vanish under kilometers of basalt. Farther away, subtle stresses accumulate invisibly. The landscape itself is transformed. Lava fields harden into step-like terraces, their appearance giving the name traps, from a word meaning stairs. These black staircases stretch for thousands of kilometers, their scale visible even today from space. Beneath them, sills cut through older rocks, cooking coals, evaporates, and organics. This contact metamorphism generates carbon dioxide, methane, and halocarbons, adding chemical burden beyond what eruptions alone release. Only took fire-meeting coal seams to add far more gas. Only took intrusion into salts to release halogens. Only took stone upon stone to alter chemistry beyond recognition. Atmospheric chemistry begins to shift. Greenhouse gases accumulate, raising global mean temperature by several degrees. Sulfate aerosols temporarily offset warming, but their residence time is short compared to carbon dioxide. Acid rain falls, carrying sulfur and halogens into soils and waters, stripping leaves from plants and leaching nutrients. Mercury vapor condenses into clays, leaving behind anomalies that modern geologists trace as markers of this period. The world breathes fire, and every exhale lingers longer than the last. The paradox of visibility and invisibility lingers. Lava flows cover vast tracts, their presence undeniable. Yet the gases, though unseen, change climate more profoundly than the rocks themselves. The visible fire draws attention, but the invisible breath alters seas, soils, and skies. This imbalance between what is seen and what is felt defines the crisis. Scientists continue to study the precise role of the Siberian traps. Were they alone sufficient to cause the deadliest extinction, or did they combine with other stresses? Some propose feedbacks. Warming oceans release methane from clathrates, further amplifying greenhouse forcing. Others suggest weakened ozone from halogen release, exposing land life to increased ultraviolet radiation. Uncertainty remains, yet consensus holds that without the Siberian traps, the Permian extinction cannot be explained. The quiet irony is that eruptions are both destructive and creative. They bury landscapes, yet they create new rock. They poison air, yet they leave behind fertile soils in distant future. They devastate ecosystems, yet they preserve in basaltic traps the story of their scale. Life perishes under their force, yet their stone endures for hundreds of millions of years, testifying silently. Warmth arrives, oxygen leaves, forests thin, rivers carry ash, lava spreads, air grows thick. Only took one province of fire to alter all Earth's systems. The Siberian traps stand as a monument to planetary transformation, a reminder that deep mantle plumes and surface life are never entirely separate. Beneath still continents, fire waits. When it rises, it remakes worlds. The gases released from the Siberian eruptions drift outward, invisible yet decisive. Carbon dioxide flows into the atmosphere in volumes vast enough to alter the balance of the entire planet. It rises not as a single exhalation, but as a sustained breath lasting hundreds of thousands of years, each pulse building upon the last. The greenhouse effect strengthens, trapping heat in the lower atmosphere. Temperatures climb across continents and seas. What was once a warm world becomes warmer still, pressing ecosystems against physiological limits they had not yet faced. To say it only took a few million cubic kilometers of basalt to change climate is to state a quiet truth. The stone remains, but the gases are what transform. With added carbon, the hydrologic cycle intensifies. Evaporation increases from ocean surfaces, and the air holds more moisture. Rain falls harder in some regions, carving rivers into swollen torrents, while other regions dry even further. Deserts within Pangaea's interior expand, their dunes advancing in shifting waves. Storms sweep across coasts with rains that carry acidic compounds, stripping leaves from trees and washing nutrients from soils. Forests begin to retreat, not everywhere at once, but gradually, in patterns recorded in pollen grains preserved in sediments. River deltas deliver increased loads of sediment into the seas, muddying once clear waters where reefs had grown. In the oceans themselves, warming causes circulation to slow. Normally, cold water sinking near the poles drives currents that refresh the deep with oxygen. In a warmer climate, this overturning falters. The difference between surface and deep layers grows sharper, and the sea stratifies into distinct tiers. Oxygen remains near the surface but does not descend into the abyss. Deep water becomes stagnant, depleted of life's essential gas. In these anoxic zones, different microbial processes take over, producing compounds toxic to most complex organisms. The abyss grows not only still, but poisonous. Warmth arrives, oxygen leaves, the irony repeating like a slow refrain across global waters. The fossil record captures the subtle prelude. Shells of marine animals begin to show stress in their growth patterns. Carbon isotopes preserved in carbonates reveal abrupt negative shifts, suggesting sudden injections of isotopically light carbon into the system. Some of this comes from volcanic emissions, some perhaps from methane released from destabilized clathrates along continental margins. If warming released methane, a greenhouse gas more powerful than carbon dioxide, the forcing would have amplified swiftly. The uncertainty remains whether this methane release occurred suddenly or gradually, but either pathway accelerates the destabilization already underway. The land shows its own testimony. Trees once dominant in humid belts grow thinner in the record. Coal deposits, built from dense forests of Glossopteris and conifers, diminish in frequency and thickness. In some regions, coal formation ceases altogether, a signal that vegetation collapsed before it could be buried and compressed into carbon-rich seams. The irony lies in how forests, long responsible for storing carbon, fade precisely when carbon floods the air in greater measure than ever before. Geochemical markers offer quiet but precise evidence. Sedimentary rocks from this interval preserve elevated levels of mercury, tied to volcanic degassing. These anomalies appear not only near Siberia but across distant basins, indicating atmospheric transport of contaminants on a planetary scale. Layers rich in nickel appear as well, trace elements carried from deep mantle sources and dispersed widely. These metal spikes in the rock record serve as fingerprints of the eruptions, markers linking climate shifts to magmatic pulses. The uncertainty that lingers is the rate of change. Carbon dioxide concentrations certainly rose, but how quickly? High-precision dating suggests some intervals of catastrophic forcing compressed into less than 100,000 years. For ecosystems accustomed to gradual shift over millions of years, such a rate would be catastrophic. It only took one rapid pulse to force the climate past a tipping point. It only took one surge of greenhouse gases to alter ocean chemistry irreversibly. It only took one cascade to shift systems that had seemed stable for eons. Three ironies recur. Diversity peaks before collapse, even as physiology grows fragile. Warmth spreads across seas, yet deep waters grow suffocating. Rain falls more heavily, yet interiors dry to desert. Each is a quiet inversion, a turning of abundance into absence. In shallow seas, carbonate production falters. Organisms that secrete calcium carbonate find the chemistry of seawater shifting against them. Increased carbon dioxide dissolves into water, forming carbonic acid that lowers pH. Saturation states of carbonate minerals decline, making it harder for corals, brachiopods, and shellfish to build skeletons. Reefs, once immense limestone structures rising from the sea floor, begin to erode rather than grow. The carbonate factory stalls and microbial communities begin to replace the skeleton builders. In time, microbialites and stromatolite-like structures will dominate, flourishing in ecological vacancy left behind. The irony of ocean acidification is stark. Seas teem with carbon, yet skeletons dissolve. Water remains abundant, yet builders falter. Life persists, but its architecture fails. What was once reef becomes rubble, and what was once complex structure becomes microbial mat. The land breathes uneasily under these new skies. Acid rain strips nutrients, soils erode, and rivers carry sediments outward. Fossil spores show increases of disturbance-adapted species, while tree pollen declines. Fires sweep more easily through drying forests, leaving behind blackened soils that wash into waterways. In the record appear spikes of fungal remains, suggesting that decay outpaced growth. Fungal spores thrive on dying organic matter, marking collapse more reliably than tree rings or pollen counts. These details show the stress of a biosphere under invisible but relentless pressure. The atmosphere itself is altered not only by carbon dioxide, but also by compounds capable of depleting ozone. Halogens released from magma-sediment interactions may have thinned the ozone layer, exposing surface life to higher levels of ultraviolet radiation. The evidence is not definitive, but some patterns in spore damage hint at increased ultraviolet stress. If true, the skies themselves became dangerous, turning sunlight from a source of life into a subtle hazard. The paradox deepens. The same eruptions that temporarily darken skies with aerosols also may have increased ultraviolet exposure by thinning protective ozone, cooling in the short term, warming in the long term, poisoning in both. It only took the chemistry of stone and gas meeting the chemistry of air and sea to unravel balances forged over hundreds of millions of years. Warmth arrives, forests retreat, seas stratify, oxygen leaves, carbon builds, skeletons dissolve. The slow breath of carbon continues, each exhalation amplifying the next. What was once a balanced Earth shifts into imbalance. a quiet turning of systems that will cascade into the deadliest extinction known. The eruptions do not end in a single outpouring, but arrive in pulses, a rhythm of fire and stillness repeated across hundreds of thousands of years. Each eruptive phase pours lava across plains and intrudes sills into buried sediments, then ceases long enough for ecosystems to attempt recovery before the next wave begins. This pattern of repetition amplifies stress, for every pause carries the illusion of stability, and every resumption erases it. To imagine the Permian world is to see a planet caught in a cycle of devastation and reprieve, as if the Earth itself exhales again and again without ever truly drawing breath back in. High-precision dating of zircon crystals from volcanic ash layers has revealed the tempo of these events. Uranium and lead isotopes measured in minute grains show pulses lasting less than 100,000 years, short enough to be catastrophic, but long enough to register in rock sequences worldwide. Each pulse aligns with negative carbon isotope excursions, sudden drops in the ratio of heavy to light carbon, signaling injections of isotopically light carbon into atmosphere and ocean. These excursions are recorded not in one basin but across multiple continents, showing that the pulses were global in effect. The irony is quiet but sharp. It only took repeated breath from Earth's mantle to alter carbon cycles more profoundly than all biological processes combined. Between pulses, ecosystems attempt to recover. Fossil assemblages show brief rebounds, with communities regaining some of their structure, only to collapse again when the next phase of eruption begins. Reefs that start to rebuild falter when seawater chemistry shifts once more. Forests that spread during intervals of calmer climate retreat when acid rains and warming return. Rivers deposit alternating layers of floodplain soil and volcanic ash. The stratigraphy capturing in stone the stop-and-start pattern of survival and loss. Each interval of calm writes a record of resilience, and each new pulse records its undoing. Geochemical traces confirm the pulsed nature. Layers of mercury spike in step with eruptive episodes, pointing to repeated releases of volatile elements. Spikes of nickel appear, another fingerprint of mantle material reaching the surface. Carbon isotopes shift downward in discrete steps rather than one smooth decline. These markers align like beats in a geological metronome, the planet keeping time with pulses of fire. The certainty is strong, yet the mechanism that synchronized magmatism and extinction remains partly obscure. Did the eruptions pace themselves according to mantle dynamics, or did feedbacks in Earth's climate magnify each phase? The mystery endures, reminding that even precise clocks do not always reveal why they keep time as they do. Three ironies flow from this pulse rhythm. It only took intervals of respite to sharpen the impact of disaster. It only took pauses to make collapse seem avoidable, only for collapse to return. It only took repetition to ensure that extinction was not an accident of one event, but the compounded effect of many. The biological consequences deepen with each wave. In marine settings, oxygen loss spreads more widely. Anoxic waters encroach upon shallows, reducing habitat for fish, mollusks, and invertebrates. Organisms that depend on oxygen-rich conditions find their refuge shrinking. Those able to tolerate low oxygen gain temporary advantage, but even they fall when conditions grow too extreme. The selectivity of extinction emerges from these physiological boundaries. Species with high oxygen demands vanish first, while those adapted to stressed environments persist a little longer. The irony is that adaptability buys time but not escape, for each pulse carries stress beyond even resilient thresholds. On land, pulses disrupt vegetation cycles. In the southern supercontinent Gondwana, Glossopteris forests decline in the record, their distinctive pollen disappearing from sediments. Coal formation halts in many regions, a sign that peat no longer accumulates under collapsing canopies. Fungal spores increase, marking decay overtaking growth. Intervals of recovery show modest forest return, but the next wave erases it again. Reptilian synapsids that had thrived in varied niches struggle as food chains unravel. Some lineages vanish entirely, while others dwindle to remnant populations. Each pulse thins diversity further, until what remains is fragile and unstable. The sedimentary record of shallow seas tells the same story. Limestone layers, once steady, break into irregular deposition. Microbial buildups appear where reefs collapse, forming stromatolitic carbonates that expand during intervals when animal reef builders fail. These microbialites, sometimes called disaster deposits, flourish not because conditions are favourable, but because competitors have vanished. Their presence is a testament to vacancy, the irony of life thriving where complexity has collapsed. The atmosphere swings between cooling and warming. During eruptions, sulfate aerosols scatter sunlight, cooling the surface for years or decades. Forests stressed by warming may briefly find relief, but acid rain falls in exchange, leaching nutrients and damaging leaves. When aerosols settle, greenhouse warming reasserts itself, driving global temperature upward by several degrees. The cycle repeats with each pulse: cooling, warming, acid rain, carbon loading. Organisms face not a single trend but whiplash, repeated swings too rapid to adapt. It only took alternating stresses to erode resilience faster than steady change ever could. The quiet mystery that persists is whether the pulse is aligned with external feedbacks. Some evidence suggests that warming released methane hydrates from continental margins, amplifying greenhouse forcing in bursts. Other evidence points to destabilization of soils and peat, releasing additional carbon. These processes may have been triggered by the volcanic pulses, or they may have amplified them. The precise interplay remains unresolved. What is certain is that feedbacks magnified the effects, ensuring that each pulse reached further into ecosystems than volcanic gases alone could have managed. The irony of repetition is that it feels survivable. Each interval of calm allows ecosystems to adapt, only for adaptation to fail when the cycle resumes. Species cling to survival during reprieves, only to be extinguished in the next wave. Sediments preserve both their persistence and their end, alternating fossils of abundance with sudden absences. The record becomes a tapestry of presence and loss, woven in rhythm with magmatic pulses. In this planetary cycle, stone, gas, and life intertwine. Lava builds staircases of basalt that endure for millions of years. Gases alter climate in ways felt immediately by forests and seas. Life, dependent on balance, struggles to endure oscillations of extremes. Warmth arrives, oxygen leaves, ash falls, forests falter. Diversity attempts to rebound, then collapses again. It only took the repetition of pulses to ensure that stress was not temporary but cumulative, pushing ecosystems toward a horizon from which they would not return. As the warmth of volcanic gases accumulates, the oceans shift into patterns they have not known before. The difference between surface and deep layers grows sharper with each increment of heat, and the mixing currents that once carried oxygen downward weaken. Stratification becomes the rule, not the exception. The surface remains habitable for a time, with light and oxygen supporting fish, mollusks, and plankton. Yet beneath this layer, the abyss grows dark and breathless. Oxygen vanishes into chemical reactions consumed by decaying organic matter that falls as rain from above. With circulation stilled, there is no renewal. The deep sea becomes a reservoir of suffocation. Only took a few degrees of warming to interrupt the overturning circulation. only took a thicker cap of warm water to cut the link between surface breath and abyssal silence, only took one shift in density gradient to transform life's refuge into its prison. In anoxic waters, new microbial processes rise. Sulfate-reducing bacteria thrive in the absence of oxygen, generating hydrogen sulfide as waste. This gas accumulates in layers, invisible yet lethal to most animals. Some scientists suggest that during episodes of mixing, hydrogen sulfide could have reached surface waters or even the atmosphere, poisoning organisms on land as well as in the sea. The evidence for this is indirect. Sulfur isotope anomalies, patterns of black shales rich in pyrite, and sudden turnovers in fossil assemblages. The mystery remains whether hydrogen sulfide ever truly breached the surface in volumes large enough to kill on land. What is certain is that the ocean depths were transformed into toxic realms where once there had been stability. The fossil record shows the consequences. Benthic communities, those that lived upon or within the sea floor, decline first. Trilobites, survivors of earlier crises, vanish entirely by the end of the Permian, their physiology unsuited to dwindling oxygen. Brachiopods, once dominant in Paleozoic seas, fade in diversity, their shells leaving behind layers that mark their final abundance. Ammonoids retreat into narrower ranges, only some surviving the oncoming collapse. Fish and marine reptiles, though adaptable, find their prey diminished, and their habitats squeezed upward into thin oxygenated layers near the surface. It is an irony repeated through time. Warmth at the surface coincides with death below, light above masking silence beneath. Chemical signals strengthen the story. Carbon isotopes show repeated negative excursions as methane or carbon dioxide enters the system, consistent with feedback loops amplifying volcanic emissions. Nitrogen isotopes reveal shifts toward processes dominated by microbes in anoxic conditions. Trace metals such as molybdenum and uranium, soluble in oxygenated water but removed under anoxic conditions, decline sharply in concentration, their absence telling the same story as fossils do. Each indicator points to oceans that have lost their breath. On land, the story is quieter but no less real. Rivers that carry sediments into the sea also carry nutrients washed from eroding soils. These nutrients feed blooms of plankton, which grow abundantly in surface waters before sinking and decomposing. Their decay consumes oxygen, feeding the anoxia below. The land and sea are not separate systems but linked in feedbacks. Soil erosion on Pangaea feeds the suffocation of Panthalassa. Forest loss on land drives collapse in the abyss. It only took erosion of a continent to strip oxygen from an ocean. It only took a storm of sediment to turn seas opaque. It only took the decay of forest to feed microbes that suffocate fish. Three ironies appear clearly in this transformation. Abundant nutrients lead not to more life, but to deeper anoxia. Microbes flourish most where higher animals cannot. Oceans filled with carbon become hostile to skeleton builders. The reversal of expectations defines the Permian seas. Some records suggest episodes of euxinia, conditions where hydrogen sulfide not only accumulates in depth, but reaches levels high enough to tint the water green or purple with photosynthetic sulfur bacteria. Such deposits are rare, but when found they imply surface waters hostile to most marine animals. The mystery is how widespread this euxinia became. Some argue for localized events, others for global expansion. The truth may be a patchwork of poisoned seas spreading across basins in waves, synchronized with pulses of volcanism. Sediments preserve black shales laid down in these intervals, their organic richness a paradox of productivity and decay. To produce such deposits requires abundant plankton growth, yet their preservation requires oxygen loss. productivity and suffocation occur together, a union of life and death in a single layer of stone. These black shales stretch across multiple continents, a silent memory of oceans that thrived and suffocated at once. Marine selectivity sharpens further. Animals with high metabolic rates vanish more quickly than those with lower demands. Creatures with efficient respiration survive longer than those that require steady oxygen. This filter is recorded not only in disappearance but in survival. Bivalves with broad tolerances persist while ammonoids collapse. Fish retreat to shallows while benthic invertebrates vanish. The pattern is not random but physiological, extinction tracing the limits of breath. The irony is that oceans once stable for millions of years collapse within tens of thousands. Circulation that seemed permanent proves fragile. Food chains that seemed abundant break when base layers shift. Refuge remains at the surface, but it is narrow and unstable. Organisms crowd into this zone until even it falters. Only took one failure of overturning to redraw the map of survival. Only took one feedback to seal off the deep. Only took one surge of nutrients to amplify suffocation. On Pangaea's coastlines, the retreat of marine communities alters shorelines visibly. Reefs crumble, carbonate platforms erode, microbial mats spread across shallows. Fossil assemblages show increased abundance of organisms tolerant of stress, such as bivalves with simple shells and short life cycles. Complex ecosystems of interdependent species give way to low-diversity communities of opportunists. In geological terms, these are disaster faunas, the first wave of survivors in a collapsing world. Their presence is not a sign of resilience, but of vacancy, the filling of voids left by extinction. The ocean crisis becomes central to the extinction. While land ecosystems falter, it is the seas that lose the majority of species. Estimates suggest more than 90% of marine life disappears, a scale unmatched in other known extinctions. Coral reefs, once builders of limestone cathedrals, vanish entirely for millions of years. Trilobites, iconic survivors of earlier ages, end here and never return. Ammonoids, resilient yet pressured, decline to a single lineage. The abyss grows quiet, its diversity erased. The irony is that oceans, birthplace of life and anchor of stability, become the heart of death in the Permian. The mystery that endures is whether hydrogen sulfide reached the atmosphere in lethal concentrations. If it did, then land life as well as sea life would have felt its poison, compounding stresses of heat, drought, and acid rain. If it did not, then the sea itself remained the primary killer. Both scenarios lead to the same outcome: a biosphere unable to withstand loss of oxygen on a planetary scale. Warmth arrives, overturning slows, surface thrives, depth suffocates, microbes flourish, animals vanish. Only took the quiet layering of warm water over cold to unravel millions of years of oceanic balance. Only took the loss of breath from the abyss to silence entire lineages. The sea, once cradle of life, becomes its tomb. Beneath the stratified oceans, where oxygen has drained away and darkness holds sway, microbial processes flourish in silence. Bacteria capable of living without oxygen dominate, feeding on sulfate and producing hydrogen sulfide as their byproduct. This gas, colourless but toxic, accumulates in the deep, forming invisible layers of poison. In these euxinic zones, conditions are hostile to nearly all animals. The deeper layers, once filled with benthic creatures, are now realms ruled by microbes, a reversal of order that unfolds quietly but relentlessly. Warmth arrives, overturning falters, and with each degree of heat the abyss becomes more alien. Only took the retreat of oxygen to invite microbes to claim what animals abandoned. only took the decay of falling plankton to fuel unseen chemistries, only took one shift in circulation to open the door to poison. The possibility remains that hydrogen sulfide did not stay confined to the deep. Some scientists suggest that during intervals of mixing, storms or currents could have brought this gas upward, reaching the surface waters. If it reached into the atmosphere, even in modest quantities, it would have posed a threat to land organisms, disrupting respiratory systems and altering atmospheric chemistry. Evidence is indirect, yet suggestive. Sulfur isotope patterns shift in ways that imply unusual cycling. Fossils of spores from plants show damage that may indicate elevated ultraviolet exposure, possibly linked to ozone depletion caused by hydrogen sulfide. The mystery endures. Did this invisible toxin remain a hidden force beneath the sea? Or did it rise into the air, compounding stresses on land? Ironies gather around this poison. Microbes flourish in conditions that destroy complexity. Nutrients increase, yet diversity collapses. Water thick with carbon grows hostile to shell builders. The irony repeats. Abundance of chemical energy translates into scarcity of animal life. The black shales deposited during these intervals record both productivity and death. Organic matter rains down from plankton blooms, settling into anoxic depths where it cannot fully decay. Instead, it is preserved, pressed into stone that millions of years later reveals conditions of suffocation. These shales stretch across regions that were once shallow shelves, showing how widespread the crisis was. Their darkness is more than absence of oxygen. It is a memory of seas that produced too much life at the surface and killed too much at depth. They are both the record of abundance and of collapse, one written into the same layer. Euxinia may also have altered the colour of shallow seas. Photosynthetic sulfur bacteria thrive in hydrogen sulfide-rich waters, creating blooms tinted green or purple. Though direct evidence is rare, some deposits hint at their presence. If correct, then coastlines of the late Permian may have glowed with strange hues, seas altered to colours alien to the animals that once swam there. The imagery is stark. Oceans turned from blue to toxic green, not through fiction, but through microbial reality. Yet whether this vision held across the globe or only in scattered basins remains uncertain. Marine ecosystems reflect the poison's reach. Benthic invertebrates vanish from layers corresponding to euxinic intervals. Shelled organisms, unable to withstand exposure, disappear entirely. Fish fossils grow rarer, their ranges constrained. Ammonoids suffer severe losses, though a few lineages endure. The pattern of selectivity persists. Physiology determines survival. Creatures with high oxygen demands fall first. Those tolerant of stress survive longest. Even tolerance, however, cannot withstand cumulative pulses. It only took repeated episodes of euxinia to press ecosystems past their breaking point. The ironies echo again. Where reefs collapse, microbial mats grow. Where animals vanish, bacteria bloom. Where skeletons dissolve, carbonate precipitates directly from chemical imbalance. Life continues, but complexity unravels. On land, indirect effects accumulate. If hydrogen sulfide entered the atmosphere, it may have combined with aerosols from eruptions to weaken ozone. Spores from ancient plants preserved in sediments show abnormalities. Their walls thickened or malformed, perhaps evidence of ultraviolet damage. This adds another layer of uncertainty, whether the skies themselves became more lethal. If forests already struggled with drought, heat, and acid rain, then increased ultraviolet radiation would only compound their decline. Each possibility is uncertain in detail, yet consistent in direction. Life on land faltered alongside life in the sea. geochemical signals strengthen the case for widespread euxenia. Sulfur isotopes show fractionations that differ from ordinary cycling, pointing to massive sulfate reduction. Ratios of molybdenum and other trace metals confirm anoxic and euxinic conditions. Iron speciation in sediments matches the same story. These converging lines of evidence do not erase uncertainty, but reinforce the central pattern. The oceans lost their breath, and in their silence, poison accumulated. 3 quiet observations stand out. It only took the flourishing of microbes to signal collapse of animals. It only took nutrient enrichment to deepen suffocation. It only took the hidden chemistry of deep seas to echo into forests and soils. Warmth arrives, poison follows, complexity recedes. The irony of microbial dominance is that it resembles Earth's earliest history. Before oxygen accumulated in the atmosphere, these seas were ruled by microbes that tolerated anoxic and sulfide-rich conditions. In the Permian, after hundreds of millions of years of animal life, the ocean returns to a state resembling its ancient self. The reversal is not permanent, but in this extinction Earth reverts briefly to its microbial past. Oceans that once birthed animals become once more a microbial domain. The aftermath is visible in recovery. After each euxinic episode, microbialites build extensive carbonate platforms, replacing reefs with bacterial structures. These mats cover shallow seafloors in thick layers, their fabrics woven by microbes rather than corals or sponges. They flourish because competitors are gone, not because conditions are favourable. Their presence testifies to ecological vacancy. This microbial world becomes the signature of the early Triassic seas, persisting until reefs slowly return millions of years later. The oceans, once full of complexity, reduce themselves to simplicity. Diversity plummets, but processes continue. Carbon cycles persist, though altered. Sediments accumulate, though darker. Microbes thrive, though animals vanish. It only took the combination of heat, stagnation, and feedbacks to bring seas to this state. It only took repeated pulses to ensure it lasted long enough to erase most lineages. It only took the silence of circulation to turn abundance into poison. Warmth arrives, oxygen leaves, plankton bloom, abyss suffocates. Microbes thrive, animals vanish. The sea transforms itself from refuge to threat, from cradle to crypt. In the stillness of deep water, hydrogen sulfide waits. A quiet force of extinction that leaves little trace beyond isotopes, black shales, and absence. What remains is the memory written in stone, the silence of oceans that once held the majority of life on Earth. The seas that once nurtured reefs now turn against them, their chemistry altered by the slow accumulation of volcanic gases. Carbon dioxide dissolves readily into seawater, combining with water to form carbonic acid. The result is a lowering of pH, a quiet acidification that erodes the ability of organisms to precipitate calcium carbonate. Builders of reefs, corals, sponges, bryozoans, algae, struggle to maintain their skeletons. Where once limestone platforms rose toward sunlight, they now begin to crumble. The carbonate factory, an intricate system of biological construction, falters. Only took the invisible shift in chemical balance to halt a process that had operated for hundreds of millions of years. Only took the exhale of volcanic carbon to dissolve stone in water. Only took a change in saturation state to collapse entire reef ecosystems. The fossil record shows this change with clarity. Reefal limestones that stretch through earlier layers vanish abruptly near the extinction horizon. Microbialites replace them, layered mats that trap carbonate grains without the architecture of coral or sponge. These microbial structures expand in shallow seas where reefs once stood, their growth not a triumph but a symptom of vacancy. Where complexity disappears, simplicity spreads. The irony is stark. Reefs collapse, but carbonate deposition continues in microbial hands. Skeleton builders fail, but chemistry still precipitates stone. The factory closes, yet a crude substitute operates in its place. Acidification does not affect only reefs. Many shelled organisms suffer the same burden. Brachiopods, once dominant across Paleozoic seas, decline steeply. Mollusks show thinning shells, their growth interrupted by unfavorable chemistry. Ammonoids contract in range, their intricate shells vulnerable to dissolution. The very architecture of marine life, built on carbonate minerals, is undone by the saturation state of seawater. It only took a global chemical adjustment to erase forms refined by evolution over vast spans of time. Geochemical evidence supports the collapse. Boron isotopes in ancient carbonates suggest a drop in pH, though precision remains debated. Carbon isotope excursions align with pulses of volcanic outgassing, correlating atmospheric carbon with changes in seawater chemistry. Sediments record a decrease in carbonate deposition, replaced by shales rich in organic material. The quiet signals align. Acidification accompanied warming, and together they stripped reefs of their builders. The uncertainty lies in magnitude. Some models suggest modest acidification compounded by other stresses, while others argue for severe shifts capable of dissolving shells in surface waters. Either way, the effect was catastrophic for organisms dependent on carbonate saturation. Ironies multiply across these changes. Water, abundant and life-giving, becomes corrosive. Reefs, which once sheltered diversity, turn to rubble. Microbes, long overshadowed by animals, rise to dominate construction. The inversion of roles defines the extinction's marine face. The loss of reefs carries consequences beyond the organisms that built them. Reefs create habitat, providing shelter, nurseries, and complex food webs. When reefs vanish, the intricate communities around them vanish as well. Fish lose spawning grounds, invertebrates lose refuges, algae lose attachment sites. Diversity declines not only because builders fail, but because the entire web collapses. Ecosystems that had thrived for tens of millions of years unravel in a geological instant. Warmth arrives, carbon builds, skeletons dissolve, habitats vanish. On land, the collapse echoes in parallel. Acid rain, formed when volcanic gases mix with atmospheric moisture, falls onto forests and soils. Leaves burn with chemical damage, nutrients wash away, rivers carry acidic loads into the sea. These rivers deliver pulses of weathered material that further stress marine systems. Soil horizons show signs of leaching, their chemistry altered. Fossil plants preserved from this interval often show damaged tissues, with cuticles scarred by acid exposure. The world of stone, gas, and water conspires against green life. Coal deposits dwindle sharply. In earlier times, thick seams of coal formed from dense forests of Glossopteris and conifers, but as acid rain and warming intensify, these peat-forming ecosystems collapse. Without forest cover, soils erode more easily, rivers grow laden with sediment, and terrestrial carbon storage diminishes. The irony is deep. Forests, long the sink of carbon, decline just as volcanic emissions flood the air with it. Coal, the silent record of past vegetation, vanishes from new strata. The factory of carbon storage closes, echoing the marine closure of the carbonate factory. Mercury anomalies in sediments confirm atmospheric disturbance. Mercury, a volatile element released in vast amounts from magmas, appears in clay-rich layers far from Siberia. These spikes align with extinction horizons, showing that volcanic emissions spread across the globe. They are not local scars but global fingerprints. Alongside mercury, nickel traces and carbon isotope shifts add chemical testimony to the collapse. Each layer of altered chemistry is a page in the record of unravelling balance. The mystery of reef shutdown is not only in cause but in duration. After the extinction, reefs do not return for nearly 10 million years. Microbial mats dominate shallow seas throughout the early Triassic, a long delay for recovery. Why did reefs remain absent so long? Was it continued environmental stress, or the absence of surviving lineages capable of rebuilding? Likely both. The long pause reminds that extinction is not a moment but a legacy, shaping life far beyond the crisis itself. 3 quiet truths emerge. It only took altered chemistry to silence builders of stone. It only took acid rain on land to erode the roots of forests. It only took vacancy to allow microbes to spread as architects. Warmth arrives, carbon dissolves into seas, reefs collapse, microbes thrive. The irony of collapse is that it reveals fragility. Reefs seem immense, but they depend on invisible chemistry. Forests seem resilient, but they depend on delicate balance of rain and soil. Oceans seem inexhaustible, but they depend on circulation of breath. When balance shifts, abundance turns to absence swiftly. In this way, the extinction reveals the quiet rules beneath life's persistence. The Permian seas become simplified landscapes. Microbialites spread, disaster faunas occupy shallows, fish crowd into oxygenated surface layers. Diversity plummets, but processes continue. Sediment still accumulates, carbon still cycles, water still flows. The difference is not the end of function, but the loss of form. Life persists, but its shapes narrow. Complexity reduces to simplicity. The ocean factory shifts from reefal architecture to microbial fabric. The land factory shifts from forests to fungi. It only took one disruption in chemistry to echo across all ecosystems. Warmth arrives, oxygen leaves, carbon builds, skeletons dissolve, reefs collapse, microbes flourish. In silence, the sea becomes a simpler world, carrying forward the memory of collapse written into stone. Above the seas, the atmosphere bears its own scars. The same eruptions that pour carbon dioxide also release sulfur dioxide, halogens, and a host of trace elements. When these gases mix with water vapor, they fall back to the surface as acid rain. The rains are not gentle but corrosive, washing through forests, soils, and rivers. Leaves lose their cuticles, their surfaces burned and scarred. Nutrients leach from the ground, carried away in runoff. Rivers swell with acidic waters that weaken plants and wash sediments toward the sea. It only took the meeting of sulfur with moisture to turn rain from nourishment into solvent. It only took the drifting of aerosols to dim sunlight above forests. It only took the return of each eruption to renew the assault on land. Forests falter under this burden. Glossopteris trees, which once dominated vast expanses of Gondwana, disappear from the fossil record near this time. Their pollen, once abundant, ceases to appear in sediments. Conifers struggle. Their growth rings narrowed or distorted, signs of stress from drought and acidic conditions. Insects that depend on these plants decline as their habitats shrink. Soils lose structure as root systems weaken, leaving ground vulnerable to erosion. Blackened horizons show signs of widespread fires, likely ignited by lightning in drying landscapes or by volatile gases in the air. The irony is clear. Forests once stabilize soil but in collapse accelerate its loss. Trees once stored carbon but in dying release it back. Vegetation once buffered climate but now magnifies its extremes. Acid rain also leaves its imprint in mineral deposits. Layers of clay preserve unusual concentrations of elements mobilized by acidic leaching, such as aluminum. These chemical anomalies stand as quiet markers of an atmosphere turned corrosive. Mercury, carried in vapor, condenses into sediments across the globe, its spikes in concentration tied to volcanic activity. Each spike is a fingerprint of the Siberian traps, preserved in stone far beyond their boundaries. Nickel too leaves its trace, sourced from mantle material rising to the surface. These geochemical signals align in sediments from Europe to China, from Australia to North America, showing that the atmosphere's burden was global, not regional. Uncertainty remains in the degree of ozone depletion. Some halogens released by intrusions into salt deposits may have weakened the ozone layer, allowing more ultraviolet radiation to reach the surface. Fossil spores display abnormalities in their walls, thickened and scarred as though damaged by radiation. Yet these patterns are debated. Are they truly signatures of ultraviolet stress or the result of other chemical assaults? The mystery lingers, unresolved. But even without ozone depletion, acid rain alone was sufficient to devastate terrestrial ecosystems. The sky became a source of harm, not nourishment. 3 ironies mark this interval. Rain, which sustains forests, turns corrosive. Aerosols that cool for a moment ensure warming for an epoch. Forests that buffer climate collapse when they are needed most. The inversion is total. What once steadied life now accelerates its decline. On the ground, spores and pollen tell the story of collapse. In layers that span the extinction, pollen from trees declines, while fungal spores surge. Fungi thrive on decay, multiplying in soils rich with dying matter. Their sudden abundance reflects the turnover of biomass into detritus. The fossil record of spores is not dramatic but precise. A quiet rise in one form and fall in another, marking ecosystem collapse more reliably than bones or trunks. The fungal spike is not the cause but the signature of widespread dieback. It only took the failure of forests to open the door for fungi. It only took the loss of growth to feed decomposition. It only took decay to leave its spores in stone. The land turns patchy, its surface stripped. Erosion increases, rivers run faster, sediments deposit in thick sequences downstream. In some basins, entire river systems change course, carrying their loads into shallow seas. This influx alters coastal waters, adding silt and nutrients that worsen marine anoxia. Land and sea collapse together, not as separate crises but as linked systems feeding one another's decline. What forests lose in soil, the ocean gains in sediment. What rivers wash away in nutrients, plankton consume in bloom. Each transfer magnifies instability. Wildfires become more common, recorded in charcoal fragments found in sediments. Drying vegetation ignites easily, leaving behind layers of ash. Fires consume what forests remain, spreading across landscapes already weakened by acid rain and heat. Insects, once abundant, decline with the loss of host plants. Synapsids and other land animals find food chains narrowing. Herbivores lose vegetation, carnivores lose prey, and both decline in fossil abundance. Entire lineages dwindle to remnants. Only took one shift in rainfall to dry forests. Only took one strike of lightning to ignite miles of vegetation. Only took repeated pulses of eruption to ensure fires never ceased for long. The irony is that fungi, fire and erosion thrive as forests collapse. Destruction becomes productive, decay becomes dominant, emptiness becomes the prevailing condition. Life continues, but in altered forms that mark absence more than presence. geochemical evidence confirms these shifts. Carbon isotopes record sharp drops tied to pulses of volcanic emissions. Mercury concentrations spike in both marine and terrestrial deposits. Sediments grow thicker with erosion products. Soils show leaching and altered chemistry. Together, these traces paint a consistent image: a land stripped of its resilience, an atmosphere burdened by toxic compounds, a cycle of destruction renewing itself with each pulse of fire. The uncertainty remains whether these effects were simultaneous or staggered. Did forests collapse everywhere at once, or did decline spread unevenly across regions? Fossil records suggest regional variation, but the end result converged. Glossopteris disappeared from Gondwana. Conifers thinned in Laurasia. Peat formation ceased across continents. Diversity fell sharply, regardless of local sequence. The global convergence was extinction. 3 quiet observations linger. It only took chemical rain to undo forests millions of years old. It only took volatile gases to mark sediments on every continent. It only took the interplay of sky and soil to cascade collapse from canopy to sea. Warmth arrives, acid falls, forests falter, fungi bloom. The atmosphere, once transparent and life-giving, becomes heavy with haze and corrosive rain. Skies dim, soils erode, rivers choke with sediment. Forests vanish, fungi rise, and land life grows thin. What remains is the memory in spores, pollen, and charcoal, a record of ecosystems undone by the very air that once sustained them. Forests unravel further as the Permian world moves deeper into crisis. What had once been expansive stands of Glossopteris and conifers weakens until collapse is widespread, leaving behind open landscapes of stumps and barren soils. Rivers, no longer bound by roots, tear through sediment in floods, carrying loads of sand, silt, and clay to the seas. Where thick peat once accumulated to form coal, no new seams appear. Coal formation, one of the great carbon sinks of the Paleozoic, ceases. The loss of coal is not simply an industrial curiosity for a distant future, but a marker of vanished ecosystems. A world that had stored carbon in dense forests and peat now loses both its vegetation and its storage system. It only took the retreat of forests to silence one of Earth's greatest geochemical cycles. It only took erosion to mark the absence of roots. It only took drying skies to erase entire landscapes of trees. In the fossil record, pollen grains decline sharply. The diversity of tree pollen falls while fungal spores increase, their abundance rising suddenly and globally. This is the fungal spike, a signal of decay overtaking growth. Fungi thrive on dying matter, and with forests collapsing, their food supply expands dramatically. Spores spread across soils, rivers, and lakes, leaving microscopic fossils that persist in sediments. Their sudden rise signals ecosystem collapse more clearly than bones or leaves. The irony is quiet. Forests vanish, but fungi bloom. Growth ceases, but decay thrives. Diversity narrows, but decomposition spreads. The spike is not victory, only the record of absence. Wildfires intensify. Drying vegetation ignites more easily, while lightning from volcanic skies sparks flames across weakened forests. Charcoal fragments preserved in sediments testify to fires, burning through landscapes on scales larger than before. Fires consume not only trees but also soils, leaving behind ash that rivers carry into basins. This cycle of fire and erosion accelerates deforestation, compounding acid rain and drought. What remains of vegetation becomes fuel for the next blaze. Only took one strike of lightning to destroy hectares. Only took one dry season to turn forest to tinder. Only took one cycle of rain and ash to ensure recovery never took hold. Animals suffer with their habitats. Herbivores lose both food and shelter. Synapsids that had once grazed or browsed widely see their population shrink. Carnivores lose prey, their ranges constricting. Fossil bones show thinning representation, with many lineages disappearing entirely. Amphibians, dependent on wetlands and rivers, decline as waterways silt and dry. The land that once supported diverse faunas becomes patchy and unstable, its ecosystems broken into fragments that cannot sustain themselves. The irony of collapse is that survivors often thrive briefly in absence. Small generalist animals that can exploit a wide range of food sources persist where specialists fail. Insects that feed on decay survive where those dependent on trees vanish. Opportunistic lineages of synapsids endure for a while in fragmented habitats. Yet these survivors are not evidence of resilience but of desperation. Their persistence marks ecological vacancy rather than stability. Geochemical markers reinforce the story. Carbon isotope shifts appear in terrestrial as well as marine sediments, showing that the carbon cycle disruption reached land. Spikes of mercury deposited in soils and lake sediments tie terrestrial stress to volcanic emissions. Nickel traces, carried by dust, settle far from their source. The air itself connects Siberian eruptions to the collapse of distant forests. Soil horizons show leaching consistent with acid rainfall, their chemistry stripped of nutrients. Each signal aligns. Fire, rain, erosion, and chemical fallout converge to unmake terrestrial ecosystems. Uncertainty remains in the sequence of collapse. Did fungi bloom globally at once, or did spores spike in stages across regions? Were wildfires more intense in some climates than others? Fossil records show regional variation, yet the outcome is consistent. Forests vanish, spores surge, animals decline. Diversity shrinks across Gondwana and Laurasia alike. The mystery is not in the direction of collapse, but in the exact path it took. The record is incomplete, yet the silence of vanished ecosystems is unmistakable. Three ironies define this moment. It only took the collapse of trees to feed an empire of fungi. It only took the absence of peat to silence coal. It only took fires to erase what rain and drought had already weakened. Growth fails, decay spreads, life narrows. The broader landscape transforms. Where forest stood, open ground erodes into badlands. Where rivers once wound through wooded valleys, braided channels of sediment cut unstable courses. Lakes shrink under heat, and wetlands vanish. The scenery becomes more barren, more desert-like, reflecting the arid conditions of Pangaea's interiors. Forest belts contract to narrow refuges along coasts and rivers, while much of the land becomes stripped. The visual contrast is stark. Once lush canopies reduced to expanses of bare ground, fungal mats and wind-blown dust. This transformation carries into the ocean. Rivers, swollen with sediment, pour their loads into coastal waters. Turbid plumes cloud the seas, altering ecosystems already strained by anoxia and acidification. Nutrients carried by erosion feed plankton blooms that, in turn, fuel oxygen loss in deeper waters. The collapse of forests thus feeds back into marine suffocation. Land and sea crises interlock, each magnifying the other. It only took the washing of soils into seas to deepen suffocation. It only took the erosion of forests to cloud reefs. It only took the linkage of systems to magnify stress beyond repair. Fossil evidence from vertebrate trackways suggest fewer large animals. Footprints become less common, their diversity narrower. Assemblages of bones in sediment show sharp declines, with many species vanishing completely. Even those that persist do so in reduced abundance. The land grows quieter, its ecosystem simplified. The fungal spike remains one of the clearest markers of this transition. Its microscopic traces are global, preserved in sediments across continents. They represent not resilience but imbalance, the triumph of decay over growth. They remain as a symbol of terrestrial collapse, a single detail that captures the broad unravelling of ecosystems. They show not only what was lost but how loss was processed, through decomposition, through decay, through the recycling of biomass in absence of renewal. Warmth arrives, forests retreat. Rain falls acidic, soils erode, trees vanish, fungi bloom. Wildfires spread, animals dwindle. Only took volcanic gases to turn rain corrosive. Only took loss of roots to release soils. Only took silence of forests to fill the air with spores. The Permian land grows sparse, its ecosystems unbound, its story written in ash, spores and stone. The record of the end Permian is not only in bones and shells but also in the metals carried into stone. Geochemical signals trace catastrophe with a precision that fossils alone cannot. Among these signals, mercury stands out. Released in vast amounts from volcanic degassing, mercury enters the atmosphere and spreads globally before depositing into sediments. Around the extinction horizon, mercury concentrations spike in clays, coals, and marine deposits on multiple continents. The spikes are sharp, sudden, and synchronous with volcanic pulses in Siberia. They form a fingerprint of eruption on a planetary scale. It only took the invisible release of a trace element to leave a lasting signal in stone. It only took a volatile carried by wind to mark the timing of collapse. It only took the persistence of mercury in sediments to show that fire spoke across the world. Nickel too carries its testimony. Derived from deep mantle sources, nickel emerges in lava and volcanic gases, dispersing into air and water. In marine sediments of the late Permian, nickel concentrations rise, correlating with microbial changes in the ocean. Some suggest that this influx of nickel stimulated methanogenic archaea, microbes capable of producing methane, further amplifying greenhouse forcing. If true, then volcanic nickel did more than leave a geochemical mark. It fueled a feedback loop that worsened warming. The mystery remains whether microbial blooms truly expanded from nickel enrichment, or whether the signal is coincidence. Yet the alignment of nickel spikes with carbon isotope shifts is difficult to ignore. Carbon isotopes themselves form one of the most direct signals. Repeated negative excursions, abrupt drops in the ratio of carbon-13 to carbon-12, appear across marine and terrestrial deposits. These excursions signal injections of isotopically light carbon into the system, consistent with volcanic emissions, methane releases, or both. The drops align with pulses of magmatism in the Siberian traps, tying biological turnover to volcanic activity. Each excursion marks a step downward in ecosystem stability. It only took shifts in isotopes to reveal the hidden breath of the planet. It only took a line in a rock to show the loss of whole faunas. It only took the chemistry of carbon to connect magma with extinction. Isotope records also reveal changes in oxygen. Shifts in sulfur and nitrogen isotopes mark transitions toward microbial processes dominant in anoxic and euxinic waters. Iron speciation in sediments points to widespread depletion of oxygen. Trace metals normally soluble in oxygenated water disappear, locked into sediments when anoxia dominates. These quiet chemical absences confirm what fossils suggest, that oceans lost their breath. Three ironies unfold within these signals. Elements that are trace in abundance become central in evidence. Metals meant to be incidental become witnesses to catastrophe. Records invisible in life become clear in death. The irony of extinction is that absence speaks most clearly, while presence leaves only faint reminders. Sedimentary layers preserve these signals in sequence. In China, the Meishan section, long studied as the global boundary stratotype for the Permian-Triassic transition, contains thin clay layers enriched in mercury and showing sharp carbon isotope excursions. In South Africa, coal-bearing strata record the same chemical fingerprints. In Greenland, shallow marine deposits align with the same shifts. Across every continent the chemistry repeats, synchronizing local collapse with global forcing. The convergence of evidence is powerful. Extinction was not regional but planetary. The mystery lies in the exact pacing of these signals. Did mercury, nickel and carbon arrive in rapid bursts or in steadier flows? Did microbial feedbacks magnify the isotopic shifts beyond volcanic inputs alone? High-resolution geochronology ties pulses of zircon crystallization in Siberian eruptions to isotope changes, yet the full chain remains partly hidden. What is certain is that metal and isotope signals align with the horizon of extinction, binding cause and effect more tightly than fossils alone. Land ecosystems echo these geochemical records. Soils leached by acid rain show altered chemistry, with unusual concentrations of trace metals mobilized into rivers. These metals eventually deposit in lakes and seas, reinforcing signals of eruption. In some places, coal seams are capped by clay layers enriched in mercury, marking the end of peat formation and the arrival of volcanic fallout in a single horizon. It only took one rain of mercury to mark the end of forests. It only took one pulse of nickel to trace the spread of microbial change. It only took isotopes in soil to synchronize with isotopes in sea. The irony is that the most catastrophic extinction in Earth's history is written not in one dramatic signal, but in subtle chemistry spread thinly across stone. Fossil losses are visible, but the geochemical record is quieter, requiring careful measurement. Yet it is this quiet record that reveals the link to fire. Fire pours lava visible across thousands of kilometers, but its gases and metals, though invisible, mark every continent. The silence of fossils is explained by the whispers of isotopes. In microbial mats that spread after reefs collapse, unusual carbonate buildups also form. These carbonates show isotopic signatures consistent with disturbed carbon cycles. They represent disaster deposits, physical structures left behind by microbial dominance in unstable seas. Their fabrics are unusual, tangled and irregular, standing apart from the ordered architecture of earlier reefs. Their chemistry, too, carries the marks of disrupted cycles. They're both a biological and geochemical record, embodying the collapse in form and in element. 3 observations conclude the role of metals and isotopes. It only took spikes in mercury to connect eruptions to extinction. It only took negative carbon excursions to confirm the magnitude of change. It only took microbial buildups to show how chemistry shaped life. Warmth arrives, isotopes fall, metals spike, ecosystems vanish. The selectivity of extinction becomes clearer through these signals. Species tied to carbonate saturation vanish first. Animals with high oxygen demand fall with anoxia. Land plants sensitive to acid rain or ultraviolet decline suddenly. Each physiological limit aligns with chemical shifts. Mercury poisons, carbon warms, oxygen declines. Physiology and chemistry interlock to determine survival. The record is not random but patterned. Extinction following the contours of vulnerability. Yet even in collapse, some lineages persist. A few ammonoids survive, perhaps aided by broad tolerances. Some synapsids endure, clinging to fragmented habitats. Microbes expand, thriving in altered chemistry. These survivors do not disprove the signals but embody them. They represent physiological thresholds met with tolerance, niches filled in absence, persistence through vacancy. Their survival is as much a record of geochemistry as the loss of their peers. The Earth system in this moment is a cascade. Eruptions release gases and metals, atmosphere warms and acidifies, oceans stratify and lose oxygen, microbes expand, animals decline, metals record the sequence, isotopes capture the shifts, fossils mark the losses. The convergence leaves little doubt that fire and chemistry together drove extinction. The mystery that remains is the exact interplay of feedbacks, the timing of methane release, the extent of ozone depletion, the pace of carbon buildup. These questions linger, but the broad pattern is certain. Warmth arrives, mercury spikes, nickel spreads, microbes bloom, carbon isotopes fall, reefs collapse, fossils vanish, diversity thins. It only took the chemistry of trace metals and isotopes to record extinction in permanence. It only took the silent testimony of elements to reveal the hand of fire. The catastrophe is not only written in stone but also in the atoms of stone, quiet witnesses to the world's greatest loss. When reefs collapse and forests thin, it is microbes that rise into prominence. In shallow seas stripped of their complex builders, microbial mats spread widely, coating seafloors in layered fabrics. These mats, composed of cyanobacteria and other microbial assemblages, trap sediments, precipitate carbonates, and grow into structures known as microbialites. In earlier times they had been overshadowed by corals, sponges, and other skeleton builders, but in the vacuum left by extinction they expand to dominate shallow environments. Their presence is recorded in thick carbonate buildups that stretch across basins, marking a world where microbial activity outpaces animal construction. It only took the absence of reefs to open space for mats. It only took the collapse of diversity to give microbes free rein. It only took vacancy to allow growth that seems abundant yet signals loss. These microbial deposits are sometimes referred to as disaster faces, a geological reminder that proliferation does not always mean health. They form where animals once built reefs but no longer can. Their fabrics are irregular, without the ordered architecture of corals, showing tangled growth that reflects opportunism rather than balance. Geochemically, they record disturbed cycles, with isotopic signatures shifted by microbial processing of carbon. They flourish in unstable seas, their success a quiet inversion of ecological norms. The irony is that life thrives most where complexity has failed. Diversity falls, but mats spread. Skeletons dissolve, but carbonates precipitate. Catastrophe creates abundance, but only of the simplest forms. The fossil record of these microbialites is striking. In the early Triassic, long after the extinction horizon, thick layers of microbial carbonates dominate shallow platforms. They persist for millions of years before reefs recover. Their endurance shows not resilience of animals, but the persistence of vacancy. Complex communities remain absent, and microbial forms continue to rule until conditions stabilize much later. The delay is one of the most notable legacies of the crisis. Not only the loss of lineages, but the long suppression of complexity. At the same time, microbial blooms expand in surface waters. Phytoplankton and bacteria respond to nutrient influx from eroded soils and decaying vegetation. Blooms grow, then die, sinking into oxygen-depleted depths where their decomposition consumes what oxygen remains. This cycle fuels further anoxia and euxenia, a feedback loop that sustains itself. Nutrients from land feed microbes in the sea. Microbes flourish, then suffocate the depths. Suffocation encourages more microbial dominance. It only took erosion of soils to feed oceans. It only took blooms to deepen anoxia. It only took the collapse of circulation to sustain the loop. Evidence for these blooms appears in unusual carbonate buildups and organic-rich shales. The shales preserve abundant organic matter, products of microbial productivity that were buried rather than consumed. Isotopic anomalies align with these deposits, showing disturbances in carbon cycling. Trace metals confirm anoxic conditions, reinforcing the link between microbial expansion and chemical imbalance. The record is layered and consistent. Where reefs vanish, microbialites grow. Where plankton blooms, oxygen falls. Where complexity declines, simplicity thrives. The irony is that microbial dominance represents both survival and regression. Microbes keep ecosystems functioning in their simplest form, recycling nutrients, precipitating carbonates, and shaping sediments. Yet their expansion marks the absence of higher life. It is survival stripped to basics, the persistence of processes without the presence of complexity. Oceans, once rich in structure, become microbial seas. Land, once forested, sends its nutrients to fuel these seas. The Earth system does not stop but simplifies. Uncertainty remains in how global these microbial buildups were. Some regions show extensive microbialites, while others display more limited deposits. Were they truly worldwide or concentrated in certain basins? Did microbial dominance persist everywhere, or did pockets of animal construction remain? The record suggests wide distribution, but details remain debated. What is certain is that microbial forms flourished far beyond their earlier range. 3 ironies mark this microbial age. Where reefs collapse, mats grow. Where oxygen fails, microbes thrive. Where diversity disappears, abundance multiplies. These inversions define the extinction aftermath, shaping seas for millions of years. The return to microbial dominance resembles Earth's distant past. Before the Cambrian explosion, microbialites were common, the primary reef builders of early seas. In the wake of the end Permian extinction, Earth reverts to this ancient state. For millions of years, seas look more like those of the Proterozoic than the Paleozoic. The collapse of complexity returns the planet to an earlier mode of life. The irony is profound. The world that had progressed to corals and trilobites falls back to microbes and mats. Progress unravels, replaced by persistence. On land, microbial dominance appears in other ways. Soils stripped of vegetation become substrates for microbial crusts. Fungi continue to proliferate on decaying matter, their spores preserved in abundance. Algal films may have grown on flooded soils, binding sediments temporarily before being washed away. These quiet microbial presences fill voids left by higher plants, yet they lack the capacity to stabilize climate or build ecosystems of comparable resilience. Their role is transitional, carrying processes forward until complexity can return. Geochemical signatures confirm microbial activity. Carbon isotopes in microbialites reflect rapid cycling. Sulfur isotopes show unusual fractionations tied to microbial sulfate reduction. Trace metals such as iron, molybdenum, and uranium align with conditions of microbial dominance in anoxic settings. These signals repeat across multiple basins, reinforcing that microbial expansion was not isolated but systemic. The uncertainty that lingers is how microbial activity interacted with climate feedbacks. Did microbial blooms release gases that worsened greenhouse forcing? Did their burial sequester carbon that stabilized climate in the long run? The balance of their role remains partly hidden. What is clear is that they shaped both the record and the recovery, holding dominance until higher life returned. The silence of complexity is written in their abundance. Microbialites stand as monuments to vacancy. Shales rich in organic matter mark blooms and suffocation. Isotopes trace microbial cycling. Fossil records thin to a few survivors, while microbes multiply. It only took collapse to return Earth to its microbial past. It only took fire, warming, and anoxia to give microbes dominion again. It only took millions of years of instability to keep them in place. Warmth arrives, oxygen leaves, reefs collapse, microbialites grow, forests vanish, fungi bloom. Simplicity thrives where complexity fails. The Earth system carries forward, but in a reduced state waiting for the long road of recovery. Extinction does not strike all species equally. In the seas, patterns of selectivity become clear as the crisis deepens. Organisms with high oxygen demands vanish first, their metabolisms unsustainable in stratified waters. Active swimmers such as certain fish and cephalopods lose habitat as oxygen retreats upward. Invertebrates tethered to the seafloor, unable to migrate vertically, disappear when anoxia expands into their ranges. Shelled organisms dependent on carbonate saturation falter under acidified conditions. By contrast, species with broader tolerances persist for a time. Bivalves with simple shells, organisms able to exploit stressed habitats, microbes that thrive in what animals cannot endure. It only took physiology to set boundaries of survival. It only took chemical thresholds to draw lines of absence. It only took metabolic need to dictate who endured. Trilobites, survivors of earlier crises, finally vanish here, their lineage extinguished after hundreds of millions of years. Their disappearance is not sudden in every basin, but complete by the close of the Permian. Brachiopods, once dominant in Paleozoic seas, decline to remnants, their niches overtaken in later times by bivalves. Ammonoids suffer severe losses, though one lineage persists into the Triassic, a fragile thread of survival that later diversifies again. Corals and reef builders collapse entirely, their ecological roles left vacant for millions of years. Sponges, once common in reef frameworks, decline to scattered survivors. Diversity shrinks not randomly, but along physiological lines. Those sensitive to oxygen, temperature, and chemistry are the first to go. On land, the same selectivity appears. Glossopteris forests vanish, but certain smaller plants persist, especially those tolerant of disturbed soils and variable climates. Conifers decline, but some hardy lineages survive in restricted regions. Among animals, large herbivores dependent on forests suffer most. Synapsids such as the dicynodonts dwindle, though a few species survive as ecological generalists. Carnivorous gorgonopsians disappear, unable to sustain themselves as prey dwindles. Amphibians retreat, their dependence on aquatic habitats leaving them vulnerable to drying rivers and lakes. Survivors are those with small size, broad diets, and resilience to unstable conditions. Extinction is not indiscriminate. It follows physiology and ecology with pitiless logic. The fossil record shows this selectivity in detail. Assemblages before the extinction are rich and diverse. Afterward they are sparse, dominated by a few opportunistic forms. In marine deposits, diverse brachiopod faunas give way to low-diversity bivalve assemblages. In terrestrial sediments, varied pollen types give way to fungal spores. In vertebrate layers, complex faunas collapse into a few generalist survivors. The pattern is consistent across regions. Diversity gives way to simplicity. Specialists give way to generalists. Complexity yields to opportunism. Geochemical signals align with this selectivity. Oxygen isotope data suggest rapid warming, a stress for organisms with narrow thermal tolerances. Carbon isotopes reveal repeated disturbances in carbon cycling, linked to physiological stress in both land and sea species. Trace metal concentrations point to toxic environments in marine basins, selecting against sensitive species. The interplay of physiology and chemistry is written into extinction patterns. It only took the narrowing of oxygen layers to confine active swimmers. It only took the loss of carbonate saturation to erase skeleton builders. It only took heat and drought to silence forests and their fauna. Ironies arise within these losses. Diversity peaks just before collapse, the fossil record showing abundance before silence. Complexity built over hundreds of millions of years disappears within a geologically brief span. Survivors thrive not because conditions are favourable, but because competitors vanish. Abundance is followed by absence, progress followed by regression, dominance followed by vacancy. Uncertainty remains in how quickly selectivity manifested. Did sensitive species vanish almost immediately, or did they linger briefly before final disappearance? Some records suggest gradual declines, others point to abrupt losses. The difference may lie in local conditions, but the global outcome is the same. Extinction is selective, not random. Physiology and habitat sensitivity determine fate. 3 quiet truths emerge. It only took metabolic demand to separate survivors from the lost. It only took chemistry to erase complexity. It only took ecological vacancy to let simplicity persist. Warmth arrives, oxygen leaves, shells dissolve, forests retreat. The irony is that survivors often define future ecosystems. Bivalves, opportunists in the Permian, later rise to dominance in the Mesozoic. The one surviving ammonoid lineage diversifies into Jurassic abundance. Synapsids that cling to survival eventually give rise to mammals. Generalists inherit the Earth, not because they were stronger, but because they endured long enough for time to reshape them. Extinction is not only about what is lost, but also about what is left behind. The survivors carry forward a reduced legacy that later becomes the foundation of new diversity. In shallow seas, disaster faunas dominate. These include opportunistic bivalves and microbial mats, thriving where complexity cannot. In terrestrial settings, smaller synapsids and hardy plants persist in fragmented landscapes. The ecological picture is one of reduction, of ecosystems simplified to bare scaffolds. Complexity will not return for millions of years. In this sense, the extinction is not an event but a horizon, a boundary between one Earth and another. Fossil layers above the extinction horizon show the new pattern. Diversity is low, abundance is skewed, communities fragile. Yet survival continues, marking the endurance of life even in collapse. The irony is that absence is more visible than presence. What stands out are the missing lineages, the empty niches, the collapsed systems. The survivors are quiet, small, often unremarkable. Yet they carry forward the thread of continuity, holding the possibility of recovery. Warmth arrives, oxygen leaves, forests vanish, fungi bloom, specialists collapse, generalists endure. The selectivity of extinction reveals not only vulnerability but also resilience. It only took thresholds of physiology to draw the line between death and survival. It only took environmental shifts to narrow the field. It only took simplicity to persist where complexity failed. The Permian world narrows to survivors defined by tolerance, not dominance. Their persistence is less triumph than continuity. They inherit a simplified Earth, carrying forward the processes of life until stability returns. In the quiet aftermath, selectivity defines what life remains, a pattern etched in fossils and confirmed in chemistry. Extinction is the silence of the many and the persistence of the few, a reduction written in physiology, ecology, and stone. The silence of extinction is measured not only in fossils but in the clocks of minerals. Zircon crystals born from volcanic eruptions contain within them uranium that decays to lead with a steady rhythm. By measuring these isotopes, geologists reconstruct time with extraordinary precision, anchoring the sequence of life's collapse to pulses of fire from the Siberian traps. In the global stratotype at Meishan in China, the turnover of species aligns almost exactly with zircon ages from volcanic layers. The extinction is not stretched across millions of years, but compressed into pulses that last less than 100,000 years each, short enough to overwhelm ecosystems that once adapted to slow changes. It only took the decay of atoms to reveal the tempo of loss. It only took crystals the size of grains of sand to measure the fall of forests and reefs. It only took the patience of minerals to tell the story of sudden collapse. High-precision uranium-lead dating shows that the main extinction pulse occurred within a window of about 60,000 years, coinciding with a surge in magma emplacement and gas release in Siberia. The boundary between the Permian and the Triassic is marked not only by fossils vanishing, but also by the geochemical spikes of mercury, carbon isotope excursions, and zircon ages that all converge. These independent lines of evidence tie extinction directly to magmatism, strengthening the link between mantle plume and biosphere collapse. The irony is quiet but sharp. Processes deep within Earth's mantle determine the fate of organisms at the surface, microbes and mammals' ancestors alike subject to the timing of crystals forming in magma. The stratigraphic record reveals details of this timing. Thin ash layers within marine sediments preserve zircons datable to within thousands of years. These ages align with the sharpest negative carbon isotope excursion ever recorded, a sign of massive carbon release. They also align with the disappearance of diverse faunas and the rise of microbial deposits. The correlation is global, appearing in China, South Africa, Greenland, and beyond. Extinction is thus not only an ecological event but a geological horizon, one that can be traced with precision across continents. The uncertainty lies in whether the extinction was truly a single short interval or a sequence of multiple pulses spread over longer spans. Some sections show evidence for earlier declines leading up to the final catastrophe, suggesting that ecosystems were stressed repeatedly before collapse. Others argue for one overwhelming event. High-precision dating continues to refine the picture, but the broad conclusion remains. The main losses occurred within a narrow band of time, synchronous with peak volcanism. Three ironies emerge from this precision. It only took crystals too small to see without magnification to measure the death of most marine life. It only took isotopic ratios invisible to the eye to reveal catastrophe. It only took patience of half-lives to show that extinction was geologically sudden. Geochemical markers reinforce this timeline. Carbon isotope excursions occur in steps that match zircon ages, each negative shift coinciding with a pulse of magmatism. Mercury spikes align with the same layers. Trace metals shift in abundance in synchrony. The convergence is striking. Fossils vanish, chemistry changes, zircons crystallize, all within the same narrow intervals. The end of the Permian is thus pinned in time with an accuracy rare in deep history. In marine faunas, the correlation is clear. Ammonoid losses coincide with dated layers, their shells ceasing to appear above horizons marked by carbon isotope excursions. Brachiopods vanish at the same level. Reef builders disappear entirely, with microbial deposits taking their place immediately above. On land, Glossopteris pollen ceases abruptly at layers that date to the same interval, replaced by fungal spores. Synapsid bones decline in abundance and diversity, many lineages ending within the same dated windows. These patterns show that extinction was not drawn out indefinitely, but sharp and aligned with volcanic pulses. The mystery that persists is how quickly environmental stresses reach global scales after each eruption. Did gases disperse within years, altering climate and chemistry immediately, or did feedbacks take centuries to amplify? The answer matters for understanding the speed of ecosystem collapse. Fossil evidence suggests that in some regions losses were abrupt, pointing to rapid impacts. Yet in other regions, gradual declines appear. Perhaps local conditions buffered ecosystems temporarily, but the global trajectory was inevitable. The speed may have varied, but the end was shared. Ironies gather here too. Diversity built over hundreds of millions of years disappears within tens of thousands. The longest-lived lineages end in the briefest spans. Extinction measured in tens of millennia feels instant in geological terms, yet unimaginably long in human terms. The mismatch of scales underscores the strangeness of deep time. Zircon ages also reveal the persistence of instability after the main extinction. Pulses of magmatism continued into the early Triassic, and with them environmental stress. Diversity did not rebound quickly but remained low, suppressed by continued eruptions and disturbed climate. The clocks of minerals show that instability lasted for hundreds of thousands of years beyond the initial crisis. Recovery was delayed not only by ecological vacancy, but also by continued perturbation. Three quiet truths emerge. It only took alignment of fossils, isotopes, and zircons to anchor extinction in time. It only took pulses of magmatism to push ecosystems beyond return. It only took tens of thousands of years to undo hundreds of millions. Warmth arrives, zircons crystallize, isotopes shift, lineages vanish. The irony is that what is most permanent in geology, stone, crystals, isotopes, records the loss of what is most fragile in biology. Minerals endure, animals do not. Elements persist, forests vanish. The record is preserved not by survivors but by silent clocks measuring decay. The end Permian extinction is thus not only a biological story but a geological one. Fossils mark the loss, isotopes mark the chemistry, zircons mark the time. Together they form a narrative where fire, stone, and breath converge. The precision of geochronology removes doubt. The deadliest extinction coincides with Earth's greatest volcanic province. The mantle rose, magma erupted, gases spread, oceans suffocated, forest collapsed, and life was reduced to remnants. The clocks of minerals preserve this sequence, silent witnesses to the fall of worlds. Warmth arrives, clocks tick, gases rise, isotopes fall, fossils vanish, zircons remain. It only took the patience of radioactive decay to measure the most sudden silence life has known. When the first years of the Triassic dawn, the world that emerges is not one of quick renewal but of lingering instability. The oceans remain warm, stratified, and oxygen poor. The land lies stripped of its great forests, its soils eroded, its rivers burdened with silt. Diversity is at its lowest in the known fossil record. Where once there had been coral reefs, microbial mats dominate. Where once trilobites, brachiopods, and ammonoids shared the seas, only a few lineages persist in shallow refuges. On land, vast Glossopteris forests are gone, replaced by scattered patches of hardy vegetation, while fungi still mark the legacy of collapse. Vertebrates are reduced to a handful of survivors, their faunas diminished and uneven. The planet is alive, but alive in the barest and most reduced sense. It only took fire to collapse the biosphere. It only took gas to thin the air and warm the seas. It only took silence of forests to show that life does not always rebound quickly. In marine ecosystems, the early Triassic is a time of disaster faunas. Bivalves expand into niches once held by brachiopods. A few ammonoid lineages persist and slowly diversify, but their shells are thinner and their abundance lower than before. Microbialites grow in shallows, producing vast carbonate buildups where reefs once flourished. These buildups persist for millions of years, reminders that complex reef ecosystems are absent. Their very presence signals vacancy, the absence of corals and sponges. The irony is plain. Carbonate platforms continue to rise, but their architecture is microbial, not animal. Abundance exists, but complexity does not. On land, ecosystems remain fragmented. Vegetation recovers slowly, beginning with opportunistic plants that tolerate poor soils and unstable climates. Conifers persist in some regions, but forests do not quickly return to their former scale. Insects diversify again, but their communities are patchy. Synapsids, ancestors of mammals, survive in small resilient lineages, while other reptilian groups persist as opportunists in simplified food chains. Large predators are absent. Ecological webs remain truncated. Trackways show smaller animals moving across barren ground, evidence of survival but not recovery. Geochemical signals confirm instability. Carbon isotopes fluctuate, reflecting continued disturbances in the carbon cycle. Mercury anomalies appear in sediments well into the early Triassic, consistent with ongoing pulses of volcanism from the Siberian traps. Oxygen isotopes reveal prolonged warmth, several degrees above pre-extinction levels, persisting for millions of years. Trace metals continue to point to widespread anoxia in the seas. The world is not simply recovering from a past event, but enduring continued stress. Uncertainty remains in how long volcanic activity truly persisted. Some argue that the most intense phase ended near the extinction boundary, with lingering emissions tapering over several 100,000 years. Others suggest that intrusive activity and degassing continued for millions of years. The fossil and geochemical record showing prolonged instability implies that stress did not vanish abruptly. Whether eruptions or feedbacks drove this continuation, the effect was the same. Recovery delayed. 3 ironies define the early Triassic. It only took survival to persist, yet survival was not recovery. It only took microbial mats to rebuild carbonates, yet their growth marked vacancy. It only took millions of years of instability to hold diversity at its lowest. The climate remains harsh. Evidence from paleosols, isotopes and plant fossils suggests aridity across much of Pangaea's interior, with hot temperatures and little rainfall. Rivers fluctuate between floods and droughts. Soils develop shallow horizons, showing poor fertility. Vegetation cover remains thin. Insects show signs of repeated turnovers, perhaps reflecting unstable environments. Amphibians, sensitive to drying, remain scarce. Terrestrial ecosystems are thus defined by scarcity and instability. In the oceans, the same pattern holds. Anoxia spreads widely, recorded in black shales that extend across basins. Evidence for euxinia continues, suggesting hydrogen sulfide remained present in many waters. These conditions suppress the return of complex faunas. Fish and invertebrates persist in oxygenated surface layers, but diversity remains low. Opportunistic lineages dominate while others wait for stability that does not arrive. The irony is that seas teem with microbes while higher animals struggle. Productivity persists, but diversity does not. The fossil record of the early Triassic reveals repeated crises, sometimes called aftershocks of the extinction. Each is marked by drops in diversity, isotope excursions, and signs of environmental stress. These crises show that extinction was not a single event but a protracted instability. Life attempted recovery, only to be checked repeatedly. It only took lingering volcanism or feedbacks to prevent stability. It only took repeated pulses to prolong absence. It only took unstable cycles to hold ecosystems in suspension. Survivors leave their quiet marks. A few synapsid lineages persist, later giving rise to more diverse forms. Small amphibians cling to habitats near water. Ammonoids diversify slowly, eventually becoming abundant again in later Triassic seas. Bivalves expand into roles once held by brachiopods. These lineages carry the thread of continuity, but their success is muted. They endure, but in a world that remains diminished. Their persistence is less a triumph than a holding action, waiting for conditions to ease. Irony surrounds these survivors. They flourish not because they were best adapted to abundance, but because they endured scarcity. Their resilience lies in tolerance, not dominance. They inherit ecosystems simplified to bare scaffolds. Their survival is the continuity of process, not the restoration of complexity. The uncertainty that lingers is how ecosystems interacted across land and sea during recovery. Did vegetation loss delay marine recovery by feeding sediment and nutrients into seas? Did marine anoxia slow terrestrial recovery by altering climate feedbacks? The records suggest interconnection, but precise mechanisms remain debated. What is certain is that neither land nor sea recovered quickly, both bound together in prolonged instability. 3 quiet truths conclude this interval. It only took continued warming to suppress diversity. It only took ongoing volcanism to renew stress. It only took ecological vacancy to delay recovery. Warmth remains, oxygen is scarce, forests are thin, microbial mats persist. The world is alive, but alive in reduced form. The early Triassic becomes a landscape of persistence rather than abundance. Diversity remains at a nadir for millions of years. Recovery is not swift but staggered, delayed by the legacy of fire and feedback. The biosphere carries forward, but as a shadow of what came before. The memory of loss is etched into reefs that are microbial, forests that are absent, faunas that are sparse. It only took the scale of the Siberian traps to delay recovery for an epoch. It only took the chemistry of carbon to suppress complexity. It only took the silence of absence to define the dawn of the Triassic. Recovery in the wake of the end. Permian extinction is unlike recovery after most other crises in Earth's history. Where other mass extinctions see rebounds within a few million years, the early Triassic remains a time of prolonged instability. For nearly 5 million years, diversity stays low, ecosystems remain fragile, and the world continues to bear the weight of past disruptions. Reefs do not return, forests remain thin, and oceans still struggle with anoxia. The biosphere does not leap back into abundance but limps forward, held in suspension by feedbacks and lingering environmental stress. It only took one mantle plume to silence whole ecosystems. It only took repeated pulses of fire to hold recovery back. It only took the persistence of disturbed cycles to delay the return of complexity. In shallow seas, microbialites dominate for millions of years, their presence the most visible marker of delayed recovery. These microbial mats are widespread across basins that once held coral reefs. Their fabrics, tangled and layered, record seas where microbes thrive but animals do not. Only later, in the Middle Triassic, do reefs slowly reappear, first small and localized, then expanding. The long gap shows that environmental conditions remained unsuitable for reef builders. Warmth, anoxia, and unstable chemistry suppressed them for millions of years. The irony is plain. Seas rich in microbial carbonates are abundant in deposits but barren of diversity. Marine faunas remain low in diversity and dominated by opportunists. Bivalves, which tolerate stress, spread widely. Ammonoids recover more slowly, their diversity increasing step by step but far below pre-extinction levels. Fish and marine reptiles begin to diversify in the Middle Triassic. But in the early Triassic their numbers remain thin. Black shales continue to accumulate in many regions, testimony to anoxic and euxinic conditions. The seas that were once the richest of ecosystems become monotonous landscapes dominated by microbes and a handful of opportunistic lineages. On land, vegetation is slow to return. Conifers persist but do not yet rebuild great forests. Smaller plants, adapted to poor soils and unstable climates, occupy patchy landscapes. Spores and pollen show gradual increases, but fungal dominance lingers in many records. Soil development is weak, erosion continues, and rivers remain heavy with sediment. Trackways and fossils of terrestrial vertebrates show that synapsids survived, but diversity is low. The largest predators are absent, and herbivore communities are sparse. Ecosystems are simplified, fragmented, and unstable. Geochemical evidence reinforces this slow recovery. Carbon isotopes fluctuate repeatedly through the early Triassic, marking instability in the carbon cycle. Mercury anomalies persist, indicating continued volcanic activity or remobilization of past deposits. Oxygen isotopes confirm prolonged warmth, several degrees above earlier baselines. These conditions suppress recovery, keeping ecosystems fragile. It only took the persistence of heat to hold back forests. It only took the repetition of feedbacks to suppress reefs. It only took prolonged instability to silence abundance. The uncertainty lies in the relative roles of lingering volcanism versus feedback loops. Were continued pulses of magmatism the main driver of instability, or did climate and ocean circulation feedback sustain stress even after eruptions waned? Evidence points to both. Intrusive activity in Siberia may have continued for millions of years, while the altered carbon cycle and weakened ocean circulation would have reinforced stress. The distinction matters less than the outcome. Ecosystems could not rebuild quickly. 3 ironies characterize this recovery. Survival is continuity, not abundance. Simplicity persists longer than expected. Diversity waits in silence while microbes hold dominion. The Earth is alive but muted, breathing shallowly after the deepest collapse in its history. In time, recovery does come. By the Middle Triassic, reefs begin to reappear, ammonoids diversify, and vertebrates expand again on land. Forests spread more widely, soils stabilize, and rivers deposit more predictable sediments. Diversity rises, though along new pathways. Some lineages lost forever, trilobites, rugose corals, glossopterous forests, never return. Others expand into vacated niches, reshaping ecosystems into forms different from before. The biosphere does not restore the late Permian world but creates a new Triassic world. Extinction is thus not only loss, but transformation. The legacy of the end Permian extinction extends beyond its immediate aftermath. By removing so many lineages, it reshapes evolutionary history. The survivors that persist become the ancestors of dominant groups in later eras. Ammonoids diversify spectacularly in the Triassic and Jurassic. Bivalves rise to prominence in the Mesozoic seas. Synapsids that cling to survival eventually give rise to mammals. Archosaurian reptiles expand, leading to dinosaurs, birds, and crocodiles. The extinction clears ecological space, and survivors evolve to fill it. The irony is that devastation becomes foundation. Vacancy is opportunity, collapse is prelude to transformation, yet the memory of the extinction remains etched in stone. Mercury spikes, carbon isotope excursions, black shales, microbialites, fungal spores, and zircon ages all converge to mark the greatest loss in Earth's history. They are not simply evidence, but reminders of how interconnected Earth systems are. Fire beneath Siberia alters air, sea, and soil across the globe. Volcanic gases dissolve reefs, stratify oceans, and poison land. Climate, chemistry, and biology interlock, each amplifying the other. The catastrophe is planetary, not local, systemic rather than singular. 3 quiet truths close this history. It only took the rising of one mantle plume to alter every ecosystem. It only took the collapse of forests and reefs to reshape all later life. It only took millions of years of recovery to show that loss outpaces renewal. Warmth arrives, oxygen leaves, forests vanish, seas stagnate. Diversity falls, microbes thrive, survivors persist. In the long silence after extinction, the biosphere waits, carrying forward the possibility of renewal. The story of the end Permian is not only about what ended, but about what continued. The planet remained, processes endured, survivors persisted. Recovery was slow, uneven, and incomplete. Yet, it happened. The Triassic world that followed was new, shaped by absence as much as presence. In its silence, Earth carried forward the memory of loss into the foundation of future life. The fires have long since cooled, the lava hardened into black staircases of stone, the oceans settled into their layered stillness. The forests that once spread across Gondwana are gone, their memory preserved only in seams of coal that end abruptly in the record. The reefs that once lifted sunlight into water are dissolved, replaced by microbial mats that leave fabrics of carbonate tangled and rough. In the silence that follows, the earth turns slowly, its breath shallow, its rhythms subdued. The Triassic world begins not with triumph, but with quiet persistence. Diversity remains low, ecosystems thin, survivors scattered. Yet the planet itself drifts forward, as it always does. Warmth lingers in the seas, rivers still cut their channels, winds still move sand across deserts. Processes endure even when forms do not. What is lost is complexity, not continuity. What remains is the slow patience of stone and water, carrying the memory of extinction into deep time. There is no conclusion, no final statement, only the ongoing rhythm of Earth itself. The basalt plains rest where they cooled, the shales rest where they settled, the fossils rest where they fell. Time gathers them into silence, into permanence, into the long stillness of geology. Life resumes in its diminished state, waiting for conditions to ease, for forests to return, for reefs to rebuild. Yet in this waiting, the Earth itself is calm. The planet holds its memory quietly, written in isotopes, metals, and fossils. It does not hurry, it does not explain. It rests in the balance of stone and sea, carrying onward through millions of years until abundance slowly returns. In the meantime, it sleeps, as it always has, in the slow rhythm of deep time.